A pleasant day, everyone. Welcome to our session for today. This is our part 6 of our discussion on limit of a function. So our main topic for today is about limit at infinity. But before we go to that topic, let us have a brief remarks of the topic infinite limits. So note that the limit of a function of x as x approaches to a is equal to positive infinity, or the limit of a function of x as x approaches to a equal to the negative infinity does not have the same meaning as the limit of a function of x as x approaches to a equal to L, where L is a real number. Okay, so take note on that. The notations limit of a function of x as x approaches to a equal to negative infinity, or the limit of a function of x as x approaches to a equal to the positive infinity are just to indicate the behavior of the function as x moves closer and closer to a. Okay? Then we have here a theorem. So we have two theorems here. If r is a positive integer, then for letter A, the limit of x divided by, the limit of 1 divided by x raised to a power r as x approaches to 0 from the left, from the right. So this is positive, so from the right is equal to positive infinity. Okay, so another theorem is the limit of 1 divided by x raised to a power r as x approaches to 0 from the left equal to, so we have two possibilities here, two possibilities, that is, it is equal to negative infinity if r is odd, and this is positive infinity if r is even. Okay, so remember this is a very important theorem that will help us evaluate limit or infinite limits. Okay, another theorem. So we have, if the limit of a function of x as x approaches to a equal to c, provided c is not equal to 0, and the limit of another function of x as x approaches to a equal to 0, then we have these following theorems. If c greater than 0, and if function of x approaches 0 through positive values, then the limit of a function of x as a limit of function of x divided by another function of x as x approaches to a is equal to positive infinity. If c is less than 0, means c is negative, and if the function of x approaches 0 through positive values, then the limit of the rational function f of x divided by g sub x as x approaches to a equal to negative infinity. Then another one is, if c is greater than 0, and if the function of x approaches to 0 through negative values, then the limit of this rational function f of x divided by g sub x as x approaches to a equal to positive infinity. And D, if c is less than 0, and if function of x is greater than 0 through negative values, then the limit of f of x divided by g sub x as x approaches to a equal to positive infinity. Okay, so you need to understand and remember this one, class, so that you can easily evaluate limits that takes this rational form. Okay, so another theorems. If limit of a function of x as x approaches to a equal to infinity, and the limit of another function of x as x approaches to a equal to c, then we have this following theorems. A, we have the limit of the sum of the two functions of x as x approaches to a equal to positive infinity. and b is the limit of the difference of the two functions f of x minus g sub x as x approaches to a equal to positive infinity also. Letter C, the limit of the product of the two function of x as x approaches to a is also equal to positive infinity, provided that c is not equal to 0. Okay? So here, provided that c is not equal to 0. And the limit of the rational function f of x divided by g sub x as x approaches to a equal to positive infinity also, provided that c not equal to 0. Okay? So remember these theorems, and you will use them. So not only during your practice or during the time that you study, but also during your exams, your quiz, and your coming quiz next week, and also your coming prelim in few weeks from now. Alright, so we have here some example. Since we had solved a lot of examples already, so you may try it by yourself. So applying the theorem, so using the theorem, try to evaluate the following limits. Alright, so you just look at the previous example in our previous session to help you solve these exercises. Okay, so now we'll go to the limit at infinity. So this is our main topic for today. So this is our part 6 on our topic limit of a function. Okay, so limit at infinity. So let us have here a definition. So let f be a function defined at every number in some interval. So we have some interval a positive infinity. So again, let us look at this interval in number line. Alright, so we have here our number line. So we have here 0. So perhaps our a is here. Okay, so assuming that our a is here, and we have to the right, we have the positive infinity. Okay, so we can take this interval here. Okay, so when you write this, we have this a positive infinity. So if you don't see any sign here, that indicates positive infinity. Alright, so you can have your a also here or anywhere from this number line. So the limit of f of x as x increases without bound is L. Without bound is it increases without bound. The limit of a function as x increases without bound is L, and that is written into this expression, that the limit of a function of x as x approaches to positive infinity is equal to L. If the value of the function approaches the value L as the value of x becomes larger and larger. Okay, so that is the condition for this. Now, for example, if you are given, say, f of x equal to x plus 4 divided by x plus 1. Okay, so what will happen if x approaches to infinity? What will be the limit of the function? Okay, so we can take this table here. Okay, so assuming our x increasing, so we have here a statement that as x increases without bound. Right, so we have here our x increasing. You have 1, 10, 100, 1000, 10,000, and so on and so forth, and you have the corresponding f of x here. Alright, and you will see the result of this rational function. Okay, so that's just an idea of what this means by x as x increases without bound. Now, let f be a function defined at every number in some interval. Okay, so this is the other Uh, so now we are on the left direction. So we have here the negative infinity. Okay, so assuming our E is here, alright, so it refers to this interval. Alright, so negative infinity and A. So parenthesis, it means excluding infinity and excluding A. Okay, so the limit of f of x as x decreases. So this time x decreases without bound. So the limit of f of x as x decreases without bound is L, and it is written in this expression. So limit of f of x as x approaches to negative infinity equals L. Right? So the condition here is that if the values of the function approach the value L as the values of x, so this is value of x, become smaller and smaller. Okay, that's the condition for this statement. For example, if you have, say, f of x equal to 2x plus 10 divided by x plus 2. So we have this rational function. Now, if the value of x decreases without bound, so like this in this table, so we have negative 1, negative 10, negative 100, and so on and so forth. So notice that the number x, or the value of x, is decreases. So, but if you look at the figure, it seems that it's increasing, but it's not, because the farther the number away from 0, from the number line, if this is our 0 here, alright, if you have here negative 1, this is our negative 1 here, and then you have negative, say, negative 10 here, okay, negative 10, and so on and so forth. So the farther the number away from 0, then the lesser is that number, or the closer is the number to 0, if that is a negative number. By the way, we're talking of negative numbers here. So the closer is the number from 0, then the bigger is that number compared to the others. Okay, so like for example, this one. So we have negative 1, negative 10, negative 100, negative 1000, negative 10,000. So the smaller number, that is the number that is nearer 0, or near 0, that is the bigger number. So among them, 1 is the biggest. Okay, that's for negative numbers. So another theorem, that if r is any positive integer, then a, the limit of 1 divided by x to the power r as x approaches to infinity equal to 0. And b, the limit of 1 divided by x to the power r as x approaches to negative infinity, so the limit is still equal to 0. So take note, whether x approaches to positive or negative infinity, so we come up here with 0. Okay, so positive, negative, but the result is equal to 0. The reason is that this is a very huge number, right? X is a very huge number, and now you have to raise this huge number by another number, so that makes this whole number a very, very big number. So 1 divided by a very, very big number, then you have a result that is equal to 0. Okay? And similarly, for this part, you have x, a large number, and then you have to raise that to another number. So you have infinity. This is a number which we cannot determine what is this, but assuming this is a very huge number, you raise that with another number, power certain number, so that makes the whole thing x, which is this time negative infinity. You raise that to a number, so that makes the whole thing bigger, much bigger. So 1 divided by a very big number, so that becomes 0. Okay, so remember this format class. As x approaches to positive infinity or negative infinity, then you have 1 divided by exponential term, so that makes the limit equal to 0. Okay, for example, if you are given here the following limit of the following, you have to evaluate. So limit of 1 divided by x to the power 6. So what will happen is that you have 1 over infinity raised to the power 6. So infinity is a very huge number raised to number 6. So that becomes a very huge number. What is that number? So we don't know. So we just represent it by this symbol, infinity. So therefore, 1 divided by a very huge number, so that will make this equal to 7. Similarly here we have x, when x approaches to negative infinity, so change this to negative infinity. So negative infinity raised to the power 3, that is still negative infinity. Then you have here infinity, so negative. So we have 15 divided by negative infinity. So a very small number, 15 is very small compared to infinity. So small number divided by a very huge number, so that becomes 0. So another here, we have 10 divided by a very huge number, that is also equal to 0. So we have 0 plus 0 equal to 0. Okay, so you have 15 divided by negative infinity raised to the power 3, that is still negative infinity, plus 10 divided by negative infinity. Okay, so we know that this is infinity. 15 divided by infinity, that is also infinity. It's negative, plus 10 divided by negative infinity. So you have now negative infinity plus negative infinity, that is 2 times infinity, or this is simply negative infinity. Okay, so the answer here is negative infinity plus negative infinity, that is still a huge number, which is negative infinity. Alright, so next we have here some simple rule or a procedure that we need to follow, so to help us solve or evaluate the limit of a rational function. Okay, so when evaluating the limit of a quotient or a rational function, so quotient at infinity, first divide both numerator and denominator by the highest power of the variable appearing in the denominator. Okay, so first step, you need to inspect the terms in the denominator and look for the term that contains the highest power. So term that contains a variable with the highest power or the highest exponent. Okay, for example, You have the limit of x, this is a rational function, x plus 4 divided by x squared plus 2x plus 5 as x approaches to infinity. Okay, so if you look at the denominator, the denominator has a degree equal to 2. Degree means the highest exponent of the variable. So in the denominator, the highest degree of the denominator is 2. So this is a quadratic equation. Here, this is a linear equation, so this is understood to be 1. Okay, so what shall we do next is to first divide both numerator and denominator by the highest power of the variable appearing in the denominator. It means that we need to divide each term individually, class. So here we have x squared as the highest uh, power term in the denominator. So you divide this by same thing as this. So therefore we have, okay, so you divide x by x squared. So sorry, x plus 4 by x squared. Of course, you still have to write the limit as x approaches to 2. Then you also do the same for the denominator. So that's why we have here denominator, divide this by x squared also. Okay, so simplifying, we have the limit. So it means here you have to divide each term, and then we have come up this. Okay, so still write the limit, the word limit. And now you can, so what's the result now? So when you divide x by x squared, that becomes 1 over x. Then you have 4 here. 4 times 4 times the limit, because this can be 4 over x squared. So this 4 over x squared can be written as 4 multiplied by 1 over x squared. Okay, so I hope it's clear. It's clear, class. Okay, so that's why we have here 4 times, and then you distribute the word limit. No? So you take the individual limit of its term. Okay, so we have here the limit of 1 over x, because x divided by x squared. Now x divided by x squared, so your first term will be 1 over x. Then take the limit of that. Then 4. So 4 over x squared. So we have here 4 over x squared. So where is 4 over x squared? This one. So 4 over x squared can be written as this. So you have the constant. You separate the constant. Then take the limit of the function, which is 1 over x squared. Okay. Then do the same in the denominator. So we have here limit of x squared divided by x squared. So this would be 1. So limit of 1 as x approaches infinity. Then plus. So you have 2. So you divide this by 2x divided by x squared. Okay, so what is left? So you can also write it this way. You have 2 times x over x squared which will give us 2 times 1 over x. Alright, so then take the limit. So you have 4 times the limit of 1 over x squared. Okay, and do the same in the denominator. Then substituting the values of x equal to infinity. Alright, so we have substituting, we have 1 over x as x approaches to infinity. So the first term here is equal to 0. Then you have 4 times 1 over 4 times 1 divided by x squared as x approaches to positive infinity. So this would be, so we already know that as x approaches to infinity, so this becomes infinity squared. So infinity squared, that is still infinity. Then you have 1 divided by infinity, so that would be 0. So you have 4 times the whole thing here, it becomes 0. Okay. Alright. Okay, so substituting the values, what you are going to see there here, class, is just look at the fraction, no? 1 over x, 1 over x squared. So when you substitute the infinity, so 1 over infinity or 1 over infinity squared, that is equivalent to 0. So that's why we have here after the substitution. So this part here, 1 over x, that is as x approaches to infinity, so 1 over infinity, that becomes 0. Okay, so similar here, 1 over x squared. So you have infinity, you squared it 1, so that is still infinity. So 1 divided by infinity, that is equal to 0. So that's why we have 4, this 4 here, and that 4, and the resulting 1 over x squared now when you plug in the value for x. Okay, so evaluating this, we have therefore 0 over 1, which is equal to 0. Okay, so that's the first example for evaluating limits of a rational function. Now, another example, you have evaluate the limit of 2x squared plus 3 divided by x squared minus 5x minus 1 as x approaches to infinity. Okay, positive infinity. So, x approaches to positive infinity. Okay, so we have to look at the numerator, look at the denominator. And what is the rule? You have to factor out, no? The purpose is to factor out the variable with the highest exponent. So in this case, or it's just the same as you divide its term. Divide its term by the highest variable with the highest exponent. So in this case, if you look at the denominator, so the highest exponent is x squared. But if you look at also the numerator, the highest, or say the degree is also 2. The denominator, the degree is equal to 2. So they have the same degree. Okay, so the technique here is to factor out. Their common is x squared, so factor out x squared. So when you factor out x squared in the first, or I'm sorry, from the numerator. So this is the numerator. So when you factor that out, so we have x squared. So what is left in the first term? That is 2, right? Because you factor out already x squared. But how about this one? So it has no x squared, or no variable. So what will happen? It just divide it by the factor. Just divide as by the factor, so that when you return it, so when you multiply it both terms, so you have 2x squared, then you have 3x squared. So x squared is equal to 1, so it will go back to 3. Okay. Then we have at the denominator, you factor out x squared. So factoring out x squared, we have for the first term equal to 1 minus. So we have 5. 5 divided by, you have 5x divided by x squared. Okay, so that becomes 5 over, sorry, you factor out x squared here. So the first term here becomes x. So when you factor out x squared, since it only have x, so when you factor this out, x squared, so you don't have x, so you have to divide it by x. So that's why you have here 5 divided by x, and minus 1 over, so divide by the common, which is x squared. Okay, so applying the limit, so the limit of, so we already divide now x squared divided by x squared, this is just equivalent to 1. When you divide x squared by x squared, that is equal to 1. So what is left is the limit of only this part here. 2 plus 3 over x squared divided by 1 minus 5 over x minus 1 over x squared. Okay, so substituting the values or plugging the value of x, that is infinity. Okay, so any number divided by infinity, that is equal to 0. So that's why we have here constant. We just copy it. Then we have here another constant, but divided by a very huge number. You square that, so that makes a much bigger number. Okay, so 3 divided by a very big number, so that is also equal to 0. And similar to this one, as also the other term. Okay, so now after substitution, so you have 2 plus 0, 1 minus 0 minus 0. So therefore, when you evaluate this, this is equivalent to 2. Alright, so this is equal to 2. So this is our limit. Okay, so the function has a horizontal asymptote at y equal to 2. So if you graph this, you will see that the function has a horizontal asymptote at y equal to 2. So equal to this one. Okay, so is it clear? Okay, so let's continue. Okay, so remember here that the function has a horizontal asymptote at y equal to 2. So if you try to graph this function using the technique of just assuming values for x and then solve for f of x. Okay, so another example here, we have another rational function and we are asked to evaluate this the limit of x cubed minus 2 divided by 5x to the fourth minus 3x cubed plus 2x as x approaches to positive infinity. Okay, so if you look at the terms at the denominator, we can say that the highest degree of the variable here is 4. Okay, so we are going to use this. We have to factor our common. Okay, so we have to factor x to the power 4. So if you look at here, so factor x cubed from each term in the numerator and x to the power 4 from each term in the denominator. So this will yield this. Okay, so still you have to copy or write the limit. Okay, so factoring out. So factoring out x cubed here. So we have 1 is left. Then since it has no x cubed here, so when you factor out, assuming that you factor out x cubed, so you have to divide this by whatever is the factor that you put out from this parenthesis. Okay, so to check, you just multiply it back. So x cubed times 1, so this becomes x cubed, the first term. Then x cubed multiply the second term. So we have x cubed numerator, x cubed at denominator. So that is equal to 1. So what is left is 2. So it will go back to this. So same with the denominator. So common is x to the fourth or factor x to the fourth. So what will left in the or what will be left in the first term? So that is only 5. But since the second term contains only x cubed, it's lacking with 1 because this is 4, this is 3. So it means you still have x in the denominator. Okay, so when you multiply it back, so x to the fourth multiplied by 3, so you have divided by x, so the x to the fourth becomes x cubed, so you have 3x cubed. Okay, similar to this one. So since it has x, but you factor out x to the fourth, so it's lacking with x to the 3. So that's why you have x to the 3 at the denominator. Okay, so now you can divide. So you have to divide the common factor, which is x cubed, and we have x to the fourth. So it means you have 1 over x here. Alright, 1 over x. So limit of the whole thing, this whole function here, rational function, as x approaches to negative infinity. Okay, so what you're going to do, you just plug in the infinity here. So any x, you put the infinity there. So we have here x cubed, so negative infinity cube, so that is still negative infinity. Alright, so 2 divided by negative infinity, so that will be 0. Okay, so you have 1 minus 2 divided by negative infinity, so that would be 0. So this part here, so this 2 divided by x cubed, when you substitute the negative infinity, so that they gave us 0. Okay, so also here we have 3 divided by x. So when you divide 3 by x, which is infinity, negative infinity, so that is also 0. That's why you have 0 here. Okay, so similar to this one, x cubed, so negative infinity cubed, that is still negative infinity. So 2 divided by infinity, that is also 0. So therefore you have only 1 minus 0 over or divided by 5 minus 0 plus 0. And here, if you substitute also infinity to x, so 1 divided by 1 divided by infinity, so 1 divided by a very huge number, that is also equal to 0. Okay, so this is 0, and the whole thing here, whatever it is, multiplied by 0, that is equal to 0. Okay, so now the function has a horizontal asymptote at y equal to 0. Okay, so next, so this is our last example. The next example will be, or the next numbers will be your exercises. Okay, so for this one, another rational function, we have 9x squared divided by x plus 2. So as x approaches to positive infinity. So again, you have to examine both numerator and denominator, factor out the common. So here, we have x squared, so factor x squared out. So we have 9 here. And then at the denominator, you have x, factor out x, so this becomes 1. So since it has no x, then you factor out its x, so you have to divide this by whatever is the factor that you take out. Okay, so you take out x, so you have to divide this by x. So we have x squared divided by x, so that will be x. And then what is left on the other part of the fraction, so you have 9 here, this is 9. Then 1 plus 2 divided by x. Then take the limit, because you are having the limit. If you have the limit of the product, then you can take the limit of each uh, factor here individually. So you have the limit of x, or you just take the limit of this one. So limit of uh, x, the whole thing here, then multiply by this one. Right, so we have 9, this is 0. So we have 9 divided by 1 plus 0. So 1 plus 0 is 1. So 9 divided by 1, that is 9. Alright, so as x approaches to infinity, so substituting, so this becomes, when this is infinity, as x approaches to infinity, so this becomes infinity. So infinity multiplied by 9, so that is still infinity. So this is positive infinity. Okay, so because this limit does not approach a real number value, the function has no horizontal asymptote as x increases without bound. Okay, so for this scenario plus, because this limit does not approach a real number value, so the function has no horizontal asymptote as x increases without bound. Okay, so I think so we still have another one here, right? So we have evaluate. This is number 4. So we have here a polynomial, right? So limit of a polynomial. So you just simply substitute the values here. So this is negative infinity, no? Approaches x approaches to negative infinity. So negative infinity cube. So that is still negative, right? Or you just do the same as what we did in the previous example. Factor out common here. So common or the highest, which is x cubed. Okay, so factoring this out. So it means you have to divide each term by x cubed. So x cubed divided by x cubed. So that is 1. Factor out this x cubed. So this one is divided by x cubed. So you have 1 over x. This one divided by x cubed. That is 3 over x squared. Okay. So we have now the limit of x cubed. So you can product, no? So you can, because here we have x is also here. So limit of the product. So you can take the individual limit of each factor. So that's why we have here limit of x cubed as x approaches to negative infinity times or multiplied by limit of this whole thing here. This whole quantity as x approaches to negative infinity. Okay, so doing the same, substituting or plugging in the value of x, that is infinity. So when this is infinity, 1 divided by infinity, that is 0. So that's why this is 0 here. So 3 divided by infinity squared, that is still infinity. So 3 divided by infinity, that is also 0. Okay, so we have here the quantity contains only 1 minus 0 minus 0, or that is equal to 1. And here we have the limit of x cubed as x approaches to negative infinity. So negative infinity cube, so that is also negative infinity. So negative infinity multiplied by 1, so that is negative infinity. Okay, so as in the previous example, this function has no horizontal asymptote as x decreases without bound. So the same reason as in the previous example. Alright, so I think that's all for this part. So you have here some numbers that you need to practice. So just apply the concept plus the theorems and the technique on how to evaluate the limits. So these are more on fractional form. Actually, there are a lot. There are still a lot of forms like the exponential form, but now we just limit our discussion on the rational function and also polynomial functions. Okay, so that's all for today, and thank you very much once again, and hope to see you in our next lecture, video lecture. Okay, so just stay safe and healthy always, and see you again next time. Good day, and bye bye for now.